Hello and welcome to Lecture 11. We're getting close to the end of the class here as we're in Unit 4. We only got 2 more lectures to go. And really, again, at the end here, I'm just trying to give you some variety. We did rip currents in the last lecture. We're going to talk about lake and sea breezes in Lecture 11. And then we're going to end with Lecture 12 and waterspouts. All right, so again, just trying to give you some variety. We've done so many topics, both in Weather Prediction 1 and Weather Prediction 2. And my goal here at the end is just to give you some good variety before we finish up with the class. Both these lectures will be shorter than Lecture 10, so let's just get right into it. All right, so some of the basics, some of the key variables when we're talking about lake sea breezes is the difference in temperature between the land and the water. All right, that's really one of the biggest factors that's going to drive this. Also, the synoptic wind. Is the synoptic wind opposing that lake sea breeze, or is it, helping that lake sea breeze? All right. If you have a synoptic flow that's opposing the sea breeze or the lake breeze, it's not going to go in as far. It's not going to move as inland. If you have a synoptic flow that's helping the sea breeze, it can go way far inland. All right. So the synoptic flow and how it either opposes or helps the lake sea breeze, and also the difference, that gradient in temperature between the land and the water, is what's driving this. It's actually pretty basic and simple, but those are the main two variables. So a few tips. If the atmosphere is unstable, lake sea breezes boundaries will often be the trigger that sets off thunderstorm development. A lake or sea breeze is basically a mesoscale cold front. So a few things with this. First, this is really tricky with temperature forecasting. As we know, temperature forecasting is hard enough, but when you have this micro to mesoscale type event occurring, I've heard some crazy stories with this. It's kind of like the marine layer in many ways. Let's say you forecast a sea breeze or a lake breeze to move, and let's focus more on the lakes because it's more of a difference there, with temperatures, especially, places like Michigan and up there in the Great Lakes region. If I was in Michigan and I was forecasting, in the early part of the summer for the lake breeze to move in 10 miles, and I thought I was going to move in far enough that where I was, that the temperatures would be more in the 60s because the air in the water is near 60. That would be my forecast. I go, okay, the lake breeze is going to move in about 10 miles. The temperature over the water is 65 degrees. That characteristic should take over where I am. So I'm going to call for temps, 65, mid 60s, maybe a tad bit higher than that, right? Well, what if the lake breeze only moves in 5 miles and you're still 85 degrees and that 65-degree air is only 5 miles away? That's how difficult it can get. You could have incredible gradients. One of my mentors, Doug Gillum, he grew up in that region, and he used to tell me stories that he was into running. He did a lot of track in high school, and he would go on these long-distance runs, and he said that he would encounter this lake breeze, and literally, like, on once he would, like, kind of jump back and forth, and on one side it was, like, 20, 25 degrees warmer with, humid, I won't call it oppressive, but sticky air, versus just going on the other side of that boundary, it was really cool and dry. All right, so it's very difficult with temperature forecasting. You need to know how far that lake breeze is going to move in because it's really going to affect your temperatures. Also, sometimes you have multiple lake or sea breezes, and a lot of times they will come together. And when they come together, when those two boundaries come together, they can trigger thunderstorms. Now, you can get thunderstorms triggered by a single boundary, but I've seen when you get multiple boundary interaction that you can really get, you can take a thunderstorm that's just a strong storm and turn it tornadic for a brief time. Okay, so there's plenty of events up in the Great Lakes where lake breeze interaction with thunderstorms has caused, it's either helped the initiation occur, or you have a thunderstorm and it locks on to one of those, or a supercell, and it locks onto one of those boundaries and really goes crazy. All right, so again, it's basically a mesoscale cold front. Watch for converging fronts from two lakes or along a peninsula. What's the best example of that? Florida, right? You can have a sea breeze coming from the Gulf and coming from the Atlantic, and when they come together, you can get explosive development. And then also keep in mind that topographic features can have a significant impact on enhancing uplift, like the Tug Hill Plateau over towards Lake Ontario. That can have an effect as well. You get this lake breeze coming in and interacts, with this topographic, or I won't call them mountains, but, elevation increase. And that could help force the air up and get convection and rainfall. All right, so that's something to keep in mind as well. It can lead to having a significant impact on enhancing uplift. When dew points are higher than the lake temperature, there is a threat for fog. Yeah, you get this cold air moving over this warm, sticky environment. You can get fog a lot of times. Again, it has some similarities to the marine layer in the West Coast for sure. When the sun shines during a typical spring or summer day, the land quickly becomes warmer while the water temperatures remain nearly constant. Convection currents develop over land in response to the rising temperatures, which causes heat near the surface to be redistributed vertically through the lowest several thousand feet above the ground. As the air of the land is warm, the air expands and becomes less dense. This produces a decrease in surface pressure over the land. Meanwhile, the pressure over the water remains nearly constant. The pressure difference or gradient between the land and water causes the air over the water near the shoreline to move inland. This is the lake sea breeze. Weak subsidence over the water and a return flow aloft directed from the land to the water completes the lake sea breeze circulation. So where does this go back? What was the first time we learned about this? Back to intro to meteorology, or what they call now weather and climate. All right, so here's a pretty simple diagram of that. Your land is warming up. You're getting this convective currents, and you're lowering the pressure while you still have this cool water, where you're getting higher pressure near the surface, high to low, and then you get a circulation aloft, and that completes this lake sea breeze circulation. Here's another visual representation of that. This is something you see in a lot of Intro to Mech textbooks. It has some good text there if you want to read through that in a little bit more detail. But pretty basic principle. It again goes back to Intro to Med, or weather and climate. You get that circulation that sets up. And obviously, what's going to make this circulation stronger? If you have a stronger gradient, if your land is much, much, much warmer than your water, then you're going to get what? A stronger sea breeze, right? If you don't have much of a gradient, then the sea breeze won't be as strong. The stronger the gradient in general, when all things are equal, the further that lake sea breeze will move in, right? Whereas the synoptic flow is also important. So, beyond just the synoptic flow, the bigger the gradient, either the stronger, more powerful that temperature gradient you're going to have, which is going to affect your temperature forecasting, and also how far it will go in, because that's really important. If you live really near the water, then you're going to be affected by this lake sea breeze. If you're far enough inland, it depends on how strong that gradient is, and then that's where the synoptic flow can either oppose this or help it, right? If you have a nice gradient and this, lake sea breeze is moving inland, but you have the synoptic flow aiding or helping it, it'll really go far inland. Whereas if you have a really nice gradient, but the synoptic flow is opposing it, it could be strong enough that even with a tight gradient, that the sea breeze won't go much, won't go far inland at all. If anything, all right. So, those are the two factors there that's important. This is a good visual way to kind of see that. All right. So synoptic flow leads into what we just talked about. The sea and land breezes are proportional to the magnitude of the land-sea temperature difference and are dependent on synoptic flow. Onshore synoptic flow favors the sea breeze, while offshore synoptic flow impedes it. All right, so the opposite is true with the land breeze. I've seen some situations, even here in the Gulf Coast, where some of these sea breezes can reach 200 miles inland with onshore synoptic flow. All right. Later on, I'm going to show you a technique to forecast how far inland these lake sea breezes will go. The tricky thing with that is that's with opposing synoptic flow. So these charts I've looked at in the literature I've looked at, it's with opposing synoptic flow. You got a strong gradient. How they counteract each other, how far inland will it go? What I'd like to see more is when you have the synoptic flow helping the lake sea breeze, how far inland will go. I haven't seen near as much on that. In my opinion, what I would do if you live near the water, either on a lake or the ocean, I would get out a journal, just like a lot of things with weather, and just write down the observations. If you have an opposing synoptic flow, I think this chart I'm going to give you is going to help you a lot, but still, nothing's perfect. It depends exactly where you live and the gradient and all. There's other things going on here, but if you did have synoptic flow helping either that lake sea breeze, I would just note that. I would be like, okay, we had this gradient and we had 10 knots of synoptic flow from the south. Let's say we're down here in like Gulfport, Mississippi, all right, down here in the northern Gulf Coast. And we were watching the sea breeze come in and we had 10 knots of synoptic flow that was helping the sea breeze. I would notice how far inland it would go and make some observations. And then I would do this over and over and over and track not just the gradient, but track what the synoptic flow is doing and just start kind of writing it down. And I think with time, it may take a while. It may take a few years to really pinpoint it, but I think you'll be able to have a good idea how far inland will go. And while on the northern Gulf Coast in the summer, we're not talking 20, 30 degree differences. I mean, the water in the Gulf a lot of times is pushing 90 degrees, but when it's 95 over 80 and it's just unbearable and you do get a sea breeze off the Gulf that brings it down to 89 over 70, while that's not great, that's still a lot better than what it could be, all right? Yeah, you don't have the bust potential like you do in the Great Lakes, but still, if you live down here and you get the sea breeze coming in and you get a little bit of relief, it's probably something people would like to hear about. And also, too, what else does the sea breeze do? As that sea breeze moves in, how far it moves in, that could be where your convection fires too, which will lead into temperature forecasting also, and also rainfall forecasting. So it's not just, how far inland or how strong it is, it's where it sets up, because a lot of times, when you have enough moisture, you get enough uplift, you get thunderstorms, all right? They're not typically overly strong unless you get multiple interactions or outflow boundaries coming together. But still, you can get a couple inches of rain really quickly if one of those storms forms right above you. During the fall, so this is with the lakes. We're focusing more with the Great Lakes here. During the stable season, which is the fall and winter into the early spring, when the lake temperatures are much warmer than the air/land around it, we will typically experience land breeze boundaries. So what does this go back to? What was an example earlier in Weather Prediction 1 where we had land breeze boundaries, and we got what? A mesovortex, right? So in the stable season, all right, so stable season, when we're getting these land breeze boundaries, you're getting that convection over the water, right, where that's the instability is at. Now, granted, it's not like a lot of times this water is very warm, but when this land is exceptionally cold and this water is, near 40, all that air rushes towards that water that's much warmer than the land around it. You get that land breeze boundary, and that's how you can get mesovortex examples, right? Here's a great example where you had two of them. You had one over Lake Ontario and one over Lake Erie. Well, a couple things with that. It's in the stable season because that's where you're going to get the convection over the water. That's how you're going to get that mesovortex example, right? So go back to this. Look, it's pretty clear over the land for the most part, right? But over the water, you get that enhanced convection because all that air is flowing, and as it's colliding, you're getting convergence and air that's being forced into the vertical, right? So that's just, an interesting example here where you had two mesovortex. Well, first things first, what does this tell you? This tells you you're probably early on in the season. You can see that December 13th because Lake Erie is not frozen over. Remember that mesovortex example I gave you? Ontario is a deeper lake, so it takes a lot longer to freeze over, where Erie is much more shallow and it freezes over. So right away you can look at that and you see the mesovortex. It's earlier in the season. I don't even need a calendar. I know it's earlier in the season. And that, the lake, because it's not frozen over, it's, again, each season's unique and there's no exact answers, but you have a better idea that you're early on. Now, if Lake Erie was completely frozen over, then I'd probably assume you're more in the later part of the season. All right, you may not be able to nail it down exactly, but it's a good indicator where you are. Plus, it's a stable season because the air is flowing towards this warmer lake, and this is where you're going to get that convection. Okay? Unstable, opposite. During the spring and summer into early fall, when the lake temperatures are much colder than the air land around it, we'll typically experience lake sea boundaries, all right? We're focusing on the lake here, so lake boundaries, lake sea, or lake breeze boundaries, I should say. All right, so what's the difference? How is this different than the stable season? No convection over the water, right? Why? Well, because the water is stable, right? It's cold, okay? Where over the land, what's happening? The land is heating, and you're getting what? Air that's rising, and you're getting convection, right? So colder to warmer, high to low, that's how you're getting these lake breeze boundaries, all right? So hopefully that makes sense. It's just basically the circulation reverses, all right? So unstable season, lake breezes, stable season, land breezes. And then another factor, look at this with the synoptic flow. You see that synoptic flow that's aligned here? Well, we're pushing that sea breeze a little bit further in, where we don't have as much of a parallel or a perpendicular influence here. And even though we have a sea breeze, it doesn't go as far inland, right? So the synoptic flow can either help it or it can oppose it, right? So depending on the flow of your synoptic scale wind can either enhance that lake breeze or keep it from going in. So again, if you're forecasting for the south shore here of Lake Ontario and the water temps were, still in the 50s or maybe up to 60, if you only thought the sea breeze was going to go this far in and it actually went this far in, it could really bust your forecast. All right, and then when you have more pronounced lake breeze boundaries, that's how you can get convection. All right, and when they interact, that's when you have a bigger threat of having more of a severe weather type situation. This is where you pretty much always think about it over Florida. It's almost like an alarm clock. You get in the afternoon, you start hearing the thunder. That sea breeze is going. Now, it doesn't always have to have them both colliding, but when they do, when you get the sea breeze from the Gulf and the sea breeze from the Atlantic, and when they collide more over the central part of the state, that's where you can get more violent thunderstorms. Again, not talking tornado outbreaks or big supercell type events, but you can get some supercells, some beautiful storms where you get this multiple boundary interaction, and then you got outflow boundaries and different things going on, and you do get tornadoes from time to time. It doesn't mean you can't, but in general, where the sea breeze will go in. Now, obviously, this water is really warm. And like I talked about with the northern Gulf Coast, it's not like you're getting a ton of relief. But still, it's a little bit better than, if the sea breeze was coming in, I would still rather be to the west of it versus the east of it, right? And where that boundary comes in, that's where you're going to start to get convection, all right? So not only it'll give you a little bit of relief on the temperatures, obviously much more pronounced in the Great Lakes than Florida, but it's also going to give you a good idea where thunderstorms are going to develop, right? So if I was looking at the models and I thought the sea breeze was going to move 20 miles inland, and the models were showing convection right along the shore but not 20 miles inland, if I felt confident I was right how far the sea breeze was going to go in, I wouldn't feel very confident that the model had the right idea on the convection and rain. So again, not just for temperature, it can help you out with rain forecasting as well. And we know how difficult it is in the summertime, anyway, right? Because, I'm not big on percentages. I'm really not, especially on the synoptic scale. If it's going to rain 2 inches, don't say 80% chance of rain. Just say rain. But in the summertime, that is the one time where percentages do make sense because you can literally be, have two places 5 miles apart and one place gets 2 inches of rain, the other place gets nothing, right? But if you can identify where the sea breeze boundaries are going to be located, it gives you an advantage and at least can help your confidence, right? You don't have to be like, well, 20%, 30%. You'll probably feel more confident. You'll feel at least 50% or more sometimes. Obviously, you really need to nail down where that sea breeze is. But if you can do that and you get better at that, it's only going to increase your confidence with rainfall as well. All right, so the shape of the coast makes sense as well, all right? The effects of the lake sea breeze are modified by coastal configurations, all right? The land and sea breezes are perpendicular to the coastline and oriented along a surface pressure gradient. So we talked about why the gradient matters, and we talked how synoptic flow can either help it or oppose it. But the shape of the coastline also can either enhance it a little bit more or it can hurt it a little bit, all right? The direction can then affect local weather along coastal towns, all right? So there's another little factor to throw in there, and this is more on the micro and mesoscale, all right? So a coastline with a concave shape will lead to divergent winds, which can reduce convection rainfall storms. Now, just because you have a concave shape of the coastline doesn't mean you're not going to have sea breeze and you're not going to have thunderstorms, but it is a little bit of a negative factor. Whereas a coastline with a convex shape will cause converging winds, which can enhance convection. So both ways, you can still easily get the sea breeze and thunderstorms and development of rainfall, but the concave will suppress it a little bit in general, where the convex will enhance it, all right? So concave in here like that, all right? So, like if you punch the wall, it's going in, concave, right? Convex, out, okay? So when we look at here, this is the land, right? Land, concave, convex, right? So the sea breeze is coming in. You can see why, if the sea breeze is coming in a convex angle, that they will probably more likely collide and enhance the convergence and the convection chances. Again, it doesn't mean you can't get rain here, but you see either moving away from each other, less chance for convergence. So you're going to get enhanced divergence here and an enhanced convergence here. All right, so just another cool little tip with that. So we're going to end with this. We're actually going to use this sheet to forecast. Now, like I talked about before, this is assuming your 950 millibar winds are offshore, okay? So opposing that lake sea breeze, okay? So for this comes from the Weather Service in northern Michigan, I believe. I think it's Gaylord, Michigan, and I'll leave a link to a paper for that to give you a little, source and more information if you'd like to look into it. But they looked at the synoptic flow opposing the lake breeze and how far inland it goes. Now, when that synoptic flow gets too strong, when it gets over about 17 knots or 20 miles an hour, then the lake breeze is not going to advance, all right? But what I would like to see is the opposite. How far will it go in if the synoptic flow is helping that lake sea breeze, all right? And that's something that I haven't seen near as much literature or people talking about, but that goes back to, just getting a notebook or a journal, noticing the gradient, the synoptic flow, and seeing how far it goes in on a daily basis. And then with time, as you kind of get a better data set, at least it'll give you a good general idea, all right? But keep in mind for this practice, again, it assumes that 950 millibar winds are offshore, all right, opposing. All right, so that's important to remember. Here's that paper I was talking about, so I'll leave that there for you to go check it out. It's from a guy named Bruce B. Smith. All right, and I believe again he's from the Weather Service in northern Michigan. I believe it's Gaylord, Michigan. All right, so now let's move into the forecasting side here. Again, kind of going back to the rip current thing where it's not overly complex, you're just adding numbers up. This is literally, you're just going on an XY axis and you're lining it up, and the chart kind of tells you how far inland it should go, all right? Now, I practiced with this with the lake breeze, and I feel like it works pretty well. With the sea breeze, I feel like it's not quite as good with that. It's a little bit more tricky there. But again, like anything, if you put the time into it and you take that notebook and you observe, you're going to get better at that as well. Even with this, don't just take it as this is going to work perfectly every time. Look at it, make sure, see how well it does work. All right, there might be some examples where it don't, and this is a great example of that because there's a lot more complexities on this than we're really hitting on because it would just go into things way beyond really the scope of what I want to get at this lecture, all right? So is the wind always going to be perfectly perpendicular to the shore? No, all right? So that's another thing to consider. Is the shoreline always going to be perfectly west to east or north to south? No, all right? So this goes into the trigonometry, and this is why you take trig, right? And the angles can change and how much, so we'll see a 20 knot winds at a perpendicular angle. Well, that's different than 20 knot winds at a 45 degree angle versus a 90 degree angle, all right? Because as the angle changes, the amount of force behind it changes, all right? So this, we're assuming a west-east orientation, so more like the northern Gulf Coast. And this goes, again, back to trig, all right? So when you're at south-southwest to south-southeast, you're at a 60 degree angle, which is, if you take the sine of that, it's 0.85. If you're southwest to southeast, you're at 45 degree angle, you're at 0.7. Again, the sine of the 45 degrees. And the sine of 30 degrees, you get a 0.5 for the west-southwest, east-southeast. Again, this is from a west to east orientation, all right? This is all I really want you to remember for the scope of this lecture. I could really make this much more difficult and make you, do vector analysis and look at the angle of the shoreline and the angle of the wind and do some complex math behind that and equations. But I just want you to understand that it's not always going to be as simple as perfectly perpendicular, okay? A lot of times there is an angle to it, and it does affect the wind speed. So with these examples here, and I'm using, again, a west to east orientation, how would that relate to 20 knots of wind? Well, in this example, I wouldn't be using a force of 20 knots. I'd be using a force of 17 knots. On this example, I'd be using a force of 14 knots. On this example, I'd be using 10 knots, all right? So that's how it can change. And changing that wind speed, either opposing or helping it, will really affect how far inland that lake sea breeze goes. All right, and then of course the gradient. Stronger the gradient, that's going to affect it as well. All right, so here's the sheet we're using. Here's our land lake delta T, so the difference, that's that delta there. So we're basically, if it's a difference of 10 degrees Celsius and the wind speeds and knots are opposing at 10 degrees, let's line it up. How far inland should the lake breeze go? It's that simple, okay? So we'll go through these, mostly very straightforward, but be careful. There's a couple things you can get tricked on, all right? It's not on purpose, but you have to read the question. So how far inland will a lake breeze penetrate with a lake temperature of 5 degrees Celsius, 41 degrees Fahrenheit, and an air temperature of 59 degrees Fahrenheit, 15 degrees Celsius? Well, first things first, how do you get a lake breeze? You need the lake to be what? Colder or warmer. You need the lake to be colder, high to low, all right? So if the lake's not colder than the land, you're not getting a lake breeze, okay? So we know it's colder here. So what's our difference? What's our delta T? We have a 10-degree difference here, all right? So 10 degrees Celsius difference, and a 950 millibar offshore wind, so it's opposing it, is 10 knots. So we have a 10-degree difference with 10 knots of 950 wind, right? So how far inland will it go? Approximately 6 miles. Well, how did we get that? Well, let's look at the chart. Here's our delta T, we got 10. Here's our 950 millibar winds at 10. And we see those when they line up. It's approximately, you see 6 miles with the line right here. It's approximately 6 miles in that example. All right, so now let's change it up a little bit. How far will a lake sea or a lake breeze penetrate with a lake temperature of 5 degrees Celsius and an air temperature of 25? So now we have what? Now the lake's colder, so we can get a lake breeze, right? It's a 20-degree difference. And the 950 millibar or offshore winds are still 10. So really now what's happened? The gradient's increased, right? The 950 opposing winds are staying the same, but the gradient's increased. So what does that tell you? You think the lake breeze will go in further, or do you think it won't go in as far? It will go in further, right? Bigger gradient. So this one's going to go in about 11 miles. Well, how did I get that? Well, let's go to 20. And we're still at 10. Before we were at 10 and 10, right? But now we've increased that gradient. So we're at 20 and 10. And it's going to go in approximately, you see 10 miles here with that line. It's a little bit past that. It's approximately 11 miles, all right? So you can just look at that and hopefully that makes sense. It's going in further because the temperature gradient has increased, all right? Now, what if the temperature gradient didn't increase, but the 950 millibar wind decreased? Let's say, it was still 10. The difference was still 10, but this went down to 5. Well, it'll still go further inland, right? So there's multiple components of this. Lake temperature of 10 degrees Celsius, air temperature of 27, so the lake is colder. Again, always make sure of that because I see people confuse that. You can have land breeze, and that's not a sea breeze, all right? So 10 to 27, that's a 17-degree difference. But your 950 millibar offshore winds are 22 knots, right? So remember, when we start getting above 17 knots, what happens? It's too strong. It's opposing it too strong, and the lake breeze will not move in, all right? So no lake breeze, offshore synoptic flow, 950 millibars, too strong. Well, how do we get that? Well, if you went to 17, and then we go back here, we're looking at 22 knots, as we go to 22 knots, you're in the no lake breeze, right? That 950 millibar offshore wind is just too powerful. It's opposing it, and it's keeping the lake breeze from moving inland, okay? All right, well, lake breeze developed with a lake temperature of 19 degrees Celsius and air temperature of 7. Whoops, something's wrong here. Wait a minute. The lake temperature is what? It's warmer than the land, right? So this is a stable season. This is a land breeze, all right? So you don't even need to look at the chart. Immediately you know the water is warmer than the land, all right? So this is a land breeze. Don't even need to look at the chart. Given an ocean water temperature of 60 degrees Celsius and an offshore wind of 15 knots, how warm will it have to get for the sea breeze to extend 4 to 5 miles inland? All right, so we know the offshore wind is 15 knots, and we know that we want the sea breeze to extend 4 to 5 miles inland, but we don't know for sure what the land temperature is. But it's easy to figure out, right? So how do we do it? We need a 20-degree difference, but let's show you how we got to that. All right, so if I'm at 15 knots and I want to go 4 to 5 miles inland, here's that sloping curve. I go 15, I go up till it hits 4 to 5 miles miles per hour, and that gives you a delta T of what? A 15-degree difference. So in this scenario with 15 knots of opposing offshore wind to go for the sea breeze to go 4 to 5 miles inland, you need a delta T of 15. All right, so let's go back here. I guess technically, if you look at it, it's more like 14. All right, but look, on the quiz, I wouldn't make it that close. It would be obvious, all right? There'd be enough of a gap that shouldn't be a big deal. But it's about 14, 15. We'll just go with 14 to keep it easier. You need a 14-degree difference, right? So it's 6 plus 14. That's how you know the land is 20, right? 20 minus 6 is 14, all right? So if we go back to that, 14 and 15, that's how you get 4 to 5. Okay, so hopefully that makes sense. All right, so now we're changing it up a little bit. Now instead of perpendicular winds, we're getting winds that are not 90 degrees. They're a little bit off, right? So if the wind is from the south-southwest at 10 knots, well, we know that's what, 0.85. So are we going to use 10 knots? No, we're going to use 8.5 knots, okay? So how far inland will the sea breeze extend if the ocean is 6 degrees Celsius and the air temperature is 26, all right? So the ocean's colder. It's definitely got a sea breeze component, but we're not using the full 10 knots. We have a 20-degree difference. The delta is 20 here. The delta T is 20, but we're not using 10 knots here. We're using 8.5 knots, all right? So the answer is about 13 to 14 miles. We're using 0.85, but let's break that down. Let's look at it, right? So 20-degree difference. All right, now what will happen a lot of times is people will go, oh, well, 10 knots. Well, again, it's not perfectly perpendicular here, all right? It's not 90 degrees, all right? So you're using 0.85, so that's 8.5 knots, okay? So 20, here's 20, and then 8.5 is somewhere in this range here. So here's 10, here's 20. Yeah, right in that 13, 14, right? If you're using 10, it'd be closer to 11, right? So I know you're saying, well, it's only a 2 or 3 mile difference, but if you have an urban area or even a city in that 2 to 3 mile difference, that could have a huge effect on temperature and precipitation, all right? So that's why it's important to understand that. And again, I'm keeping this simple. I'm only giving you a few different angles here. In reality, it's much more complex because coastlines are not perfectly west and east, and wind changes, obviously, all right? But I'm just at least giving you the baseline how to do this. If you're adjacent to a west to east coastline, the wind is from the southwest at 20, so it's not perpendicular, southwest 0.7. So we're using 20 knots? No, we're going to be using 0.7 of that, which is 14 knots. How far inland will the sea breeze extend? Same difference here. We had 20-degree difference, all right? So 20-degree difference, but now we're using 14 knots, all right? So the answer here is 5.5, and we're using 0.7. So let's look at it. Let's make sure that makes sense, all right? So again, we're using 14 knots, not 20 knots, because we're using 0.7 here, okay? So 20-degree difference, 14 knots. We go up here. We see that this is 6 miles. We see this is 4 or 5 miles. Going back to that, about 5.5 miles. All right. Again, I wouldn't go 6 miles, 5.5, 5 miles on the quiz. It'd be like 10 miles, 5.5. It'd be enough of a gap that you really shouldn't miss it. Okay. So hopefully that makes sense. All right. So now it's west southwest, right? So that's 0.5. So we're using 10 knots. All right. Still, we're using that west-east orientation just to help you visually see this and keep this simple. How far inland will a lake breeze extend if Lake Ontario is 10 degrees Celsius and air temperature rises to 25, all right? So 15-degree difference, but we're not using 20 knots, we're using 10 knots, all right? So the answer here is about 8 to 9 miles inland, and we're using 0.5. Again, 15 delta T with 10 knots, not 20, all right? So let's look at that. 15 delta T, 10 knots. We see this is 10, we see this is 6. Yeah, I mean, that's in that 8 to 9 mile range, right? But if you didn't use the 0.5, if you used 20 knots, what would have happened? You would have gone over here and you would have said no lake breeze, when in reality the lake breeze was going to come in 8 to 9 miles. You would have really busted your forecast bad that day by not understanding this principle and using trig, all right? So it is important. Again, I'm keeping this very simple as a whole just to kind of give you, versatility and just give you an advantage and an edge and at least show you the foundation how to get this going. But it is a little bit more complex because it's never going to usually be a perfect angle, and usually your coastline isn't perfectly west to east, all right? So just keep that in mind. All right, so a couple more here. Lake temp of 5, air temp of 25, so it's colder. We can do this. We can get that lake breeze, 20-degree difference. but 7 knots. So this is an example where you're more you're having a nice gradient and you have a weak offshore component. So this should go pretty far inland and about 20 miles. That's the furthest one we've had yet, right? So let's look at that, 20 and 7. All right, so delta T at 20, only 7 miles of opposition here. 7 miles per hour opposition, 20 miles, all right? So you can see when you have a strong gradient and you don't have the opposing 950 winds, it can go pretty far in. Well, imagine how far it would go in with a 20 difference and you had 20 knots of synoptic flow helping you. That's when you get the crazy, it goes in hundreds of miles, right? So again, you'll want to just, wherever you are, get a notebook and observe that. All right, so here's another example here. How far inland will a lake breeze advance with a lake temperature of 0 degrees Celsius and air temperature 20 degrees? All right, so your lake is colder than your land, but your offshore wind component is what? It's too strong, right? So we know when it's stronger than 17 knots, it's not going to happen. Also, what's another problem here? The lake's frozen over, so I wouldn't try to give you anything like that to trick you, and that's why I added this just to make it obvious. But that's something to keep in mind. If the lake is frozen over, it's kind of hard to get a lake breeze, right? So no lake breeze, offshore component is too strong, plus the lake is frozen over, right? You can see that here, even with that 20-degree gradient, because we're at 20 knots, no lake breeze. How far inland will a lake breeze advance with lake temperature 22 and air temperature 9 degrees? What's the problem already with this? Well, the lake temperature is what? It's warmer than the land. So is this a lake breeze? No, this is a land breeze. Don't even need to look at the chart. All right, so now what do? We just reversed it, right? So now the lake is colder than the land. So what do we have? A 13-degree difference. We also don't have much offshore component. We only have 5 knots, all right? So this one will go 17 to 18 miles in. All right, we got 13, and then what was the 955? So we're looking at 13. We're going to 5. Not quite 20, but, in that 18-mile range, 17, 18-mile range. All right, so on this one, gradient might not have been as strong, but the opposing wind was less, right? So it helped to go in even further. And then here, lake breeze, how far a lake breeze advance with lake temperature of 13, air temperature of 19, so much less of a gradient, and you have much more of an opposing factor. So what does that tell you before you even look at anything? You think the lake breeze will go in further or shorter? It's not going to go in near as far, right? So about 1 to 3 miles in this example. So you can just look at it and kind of tell before you even look at the actual chart. So 6 and 15, we got 6 difference, and we got 15. We're in that 1 to 3 mile range. All right, so last couple here, I think this might be the last one. Ocean water temperature of 5, and you have offshore wind of 10 knots. How warm will it have to get for a sea breeze that extends 6 miles? So we already have practice on that one. 10 knots, we know we wanted to go 6 miles inland, right? So the answer is about 15, but let's look at it. All right, so 10 knots, we wanted to go 6 miles in, so here's that curve there. So what delta T do you need? Approximately 10, all right? So going back to this, how would you get a delta T of 10? You would want what? You would want your land to be 15 degrees Celsius. 15 minus 5, and the water's colder, so you can get a lake breeze. 15 minus 5 is 10, with 10. Let's go back again. 10 and 10, 6 miles, all right? So hopefully that makes sense. All right, so hopefully going through these was helpful and it's good practice. Again, I'm just giving you the overarching, basic variables and details. But again, I'm just trying to make you more variable, or not more variable. I'm trying to make you more versatile. All right, so hopefully you found this kind of interesting and fascinating, because it really can affect temperature forecasting and precipitation forecasting. And if you can start getting a handle on this, you live near the Great Lakes or the ocean, you can really fine-tune your forecast and do a much better job with it. All right, well, I'll be back here shortly with Lecture 12.